In this video, I'll be going over the solution to the 2021 AIME 1 problem 10. So we're given this really complicated sequence, this recursive equation, where we have a to the a k, and we're given that the first term is 2020 over 2021, and for k greater than 1, a over k equals m over n for relatively prime positive integers m and n. So that means that the fraction, before we move on to the next term, the fraction is going to be completely simplified, where the numerator and denominator share no common factors. And then after that simplification process is done, then we add 18 to the numerator, and we add 19 to the denominator. And so we're asked to determine the sum of all positive integers j, such that the number aj can be written in the form of t over t plus 1 for some positive integer t. Okay, so let's start off with some values that we do know for j. We know that j equals 1 works because it's given in the problem. A1 equals 2020 over 2021. And we also know that a of 2 works because if we just do the calculation, then we get 2038 over 2040. And that simplifies to 1019 over 1020. And these two have a difference of 1 for t equals 1019. And so a to the 2 is a valid case, right? Okay, so let's take a of 2 and let's write a recursive equation starting from a of 2. So let's say a of 2 plus x equals 1019 plus 18x over 1020 plus 19x. Now, this isn't going to work for all values of x because in our recursive equation, we have to fully simplify our fraction before we add 18 and 19. So what this means is that the numerator and the denominator, we basically have to have these, we have to have these relatively prime to each other. So that way they don't share any common factors, and the fraction is completely simplified, and we can continue adding 18 to the top and 19 to the bottom, right? Okay. So, and now for this fraction simplifying part, this is actually really basic, right? So if we have a fraction a over b, let's say, how are we going to simplify this into like the most common terms, right? What we do is we take a over the greatest common factor, greatest common denominator of a and b, and we do over b over the greatest common denominator of a and b. And that's how we simplify any fraction where we can cancel out values. So 4 over 8, for example, the GCD here is 4, so we do 4 over 4 over 8 over 4, and that gives us 1/2. So that's basically how we simplify our fraction, right? Okay, since the numerator and denominator have to have a difference of 1, then we can write an equation with GCDs. We have 1019 plus 18x over the greatest common denominator of 1019 plus 18x, and the other value, which is 1020 plus 19x. 1020 plus 19x. Plus 1, right? Because this is our, right? That's our numerator. So this is our numerator when fully simplified, and that equals 1020 plus 19x over the greatest common denominator of, again, the same two numbers, 1019 plus 18x and 1020 plus 19x. Okay, so we have an equation to work with. Now, the greatest common denominator expressions are obviously very complicated. There has to be a way to kind of simplify them. And if you know what Euclid's algorithm is, then it's pretty obvious to see how to apply it here. But if you don't, I'm just going to go over it real quickly. So Euclid's algorithm is basically, if we have the GCD of two numbers a and b, then we can basically, this same GCD will be equal to the GCD of the numbers a, and then we can subtract any number of multiples of the other numbers. So if I want to say find the GCD of a and b, then that's the same as the GCD of a and the GCD of b minus some number of multiples of a. So for example, if I had like the GCD of x and x plus 1, right? What I can do is I can subtract one multiple of x from this side, and so then I get the GCD of x and x plus 1 minus x, which is 1. Right? So this gives us a really cool way to simplify complex-looking greatest common denominator expressions into really workable examples, right? Like GCD of x and 1, like that's just going to be 1. So if we take our very complicated GCD expression here, we have GCD of 1019 plus 18x and 1020 plus 19x. What we can start off with doing is subtracting one multiple of this side from this side, and so then we get the greatest common denominator of 1019 plus 18x. And then 1020 minus 1019 is 1, and 19x minus 18x is just x. So x plus 1 and 1019 plus 18x. Again, still very complicated. So now what we're going to do is we're going to subtract 18 times of this side from this side. And so 18 times x plus 1 is 18x plus 18. And so that gives us GCD of 1019 minus 18 is just 1001. And 18x minus 18x is 0, so we just have 1001. And we have x plus 1. Okay, cool. So we simplified this really complicated looking GCD expression into something very workable. Right? And so now let's write our new equation. So our new equation is 1019 plus 18x, 1019 plus 18x, over the GCD of x plus 1, comma 1001. And then we add 1 to this, so this plus 1 equals 1020 plus 19x. 1020 plus 19x. And we divide that by the greatest common denominator of x plus 1 and 1000. Okay, and if we simplify this expression, then we get x plus 1 equals the GCD of x plus 1 and 1001. So what this is saying is that x plus 1 has to be a factor of 1001. And the factors of 1001, I'm pretty sure it's equal to 7 times 11 times 13. Right, so now we have x plus 1 can be either one of these three. But in our problem, what we're doing is we're simplifying this expression into like the smallest possible fraction. And so if we do that, then if we do something after the smallest value of x plus 1, which in this case is 7, then our fraction is going to simplify, because now we have a common factor between the numerator and denominator, and so our original equation becomes completely useless, because this equation no longer works, because now these two, the numerator and denominator, are simplifiable, and we can cancel them out. So this equation is going to sort of veer off track, because once we get to x equals 7, then, or x equals 6, then our equation becomes simplifiable, and then we have to use a new equation, because now we're working with two completely different numbers. 1019 and 1020 will be replaced with some other numbers in our new simplified fraction, right? So x plus 1 must be equal to 7, because we can't have anything more than 7. So if x plus 1 equals 7, then x equals 6. And if we look back at our original equation, if x equals 6, then j is 2 plus x, which in this case equals 8. So j equals 8 for this case, right? And so now we can do the same exact thing, but for a of 8. So we know that a of 8 equals 1019 plus 18 times 6 over 1020 plus 19 times 6. And if we simplify this, then we get 1127 over 1134, and we can simplify these further to finally get 161 over 162. So j equals 8 does in fact work. And now we're working with this whole new fraction. So what we can do is now we can write the same equation for j, so for 8. So we can have a of 8 plus x equals 161 plus 18x over 162 plus 19x. And this equation, all these recursive equations we're writing, are only going to hold true until this fraction becomes reducible. Again, like I said before, because if this fraction becomes reducible, then our equation becomes invalid and these numbers change. Because you can see that our numbers change from 1019 to 161, and likewise for 1020 and 162. So we have to keep that in mind. And so what that means is we have to always look for the smallest possible value of x that satisfies our conditions, right? Okay, and so by our other problem, we have the GCD of 1001 and x plus 1, right? We don't really want to keep simplifying this and repeat the Euclidean algorithm process for every single equation we have. So we can kind of notice a pattern. If we take the numerator number, which is in this case 1019, and subtract 18 from it, then we get 1001, and then we're always going to have x plus 1 as the second number. So in this case, we have 161 here, so we're just going to subtract 18 from that, which is 143. And so we have the GCD of 143 and x plus 1 equals x plus 1. So x plus 1 has to be the smallest factor of 143, right? And so 143 is equal to 11 times 13. So x plus 1 has to equal 11. Again, we're looking for the smallest value, because once x equals 11, all the values from x equals 1 to 11 will keep this fraction as it is, but once we get to 11, it becomes reducible, and like I said, these two numbers will change. So in this case, x equals 10, and if x equals 10, then by our definition of j is going to be equal to 18. So we have j equals 18. So we have 8, and we have 18, and we also have 2 and 1. Okay, and so now we can calculate j of 18 and make another equation. So we have a of 18 equals 161 plus 180 over 162 plus 190. This simplifies to 341 over 352. And that's going to simplify to 31 over 32. Okay, and so now we have a new equation. Now we have a of 18 plus x equals 31 plus 18x over 32 plus 19x. Again, we're looking for the smallest possible value of x. We're going to subtract 18 from 31 to get the GCD of 13 and x plus 1 equals x plus 1 equals x plus 1. So x plus 1 has to be the largest factor of 13. Smallest, which in this case is 13 itself. So x equals 12. And if x equals 12, then j is going to be equal to 30. Right, and so we can do another equation. So we find a of 30. A of 30 is equal to 31 plus 18 times 30 over 32 plus 19. Oh, sorry, not 30, 12, because it's x. My bad. 18 times 12 over 32 plus 19 times 12, which is equal to 247 over 260, which equals 19 over 20. Now, if we stop here, look at 19, right? If we subtract 18 from 19, then we're going to get 1. And so x is just going to be 0. And if we have 0 here, then we're going to have a of 0 plus x equals some fraction. like some number c plus 18x over d plus 19x. But this is just going to leave us with c and d, because the only value of x that works is x equals 0. So we know that we're done. We can't really go beyond this equation. So we stop here. And so we know that our values for j end at 30. So we have that all of our possible values of j are 1, 2, 8, 18, and 30. These are all of our possible values of j. And so if we add them up, then we get 11 plus 18 plus 30, and that gives us our final answer of 59.